So the first point is frames of reference. Frames of reference. So what are frame of reference or frame of reference? It is a coordinate system which we use to observe any physical event or to take measurements of any physical event. So frame of reference is nothing but a coordinate system. We know every body is in a any body in a motion. When we say a body is in a motion, if it changes its position with respect to surrounding. So when we say a body is in a motion, it changes its position with respect to surrounding. Or when we say it is at rest, when it does not changes its position with surrounding. So when a body is at rest, first let's take rest. So it does not change its position with respect to surrounding. Okay, and a body is in motion when it changes its position with respect to surrounding. Okay, with respect to surrounding. Okay. So when we say a body is in motion, it changes its position with respect to surrounding, and it is at rest when it does not change its position with respect to its surrounding. So that surrounding is a frame of reference. Now let's consider Eiffel Tower. Now Eiffel Tower appears to be rest. In which frame? In Earth frame. Okay, in an observer on Earth. This is Earth. This is Eiffel Tower. Okay, so an observer X on Earth will observe Eiffel Tower is at rest according to this surrounding, this Earth. Okay, now let's take observer Y on Moon. Observer Y on Moon. Now he will observe that Eiffel Tower is not at rest position. Okay, because it is changing its position with respect to surrounding. Now the surrounding is whole solar system, we can say, or other than Earth, or the reference frame is used as Moon. Okay, so he will observe that Eiffel Tower is moving with Earth, and hence it is also moving. So he will observe that Eiffel Tower is not at rest, but observer on X is observing that Eiffel Tower is at rest. So he is considering Earth as a reference frame, and this observer is considering Moon or the solar system as a reference frame. Now let's consider so when body is in a rest, it does not changes its position with surrounding, and if it is in a motion, it changes its position with surrounding. Now consider a lift. From this example, we will go to the frame of reference. Okay, the actual meaning of frame of reference. There are two types of frame of reference: inertial and non-inertial. We will see them in details. Inertial and non-inertial. Okay, so we will start with example. With example, we will get the idea very clear. Okay, so let's take a lift. Okay, let's take a lift on top floor of a building. Okay, top floor of a building. Here it is a lift on top floor of a building. Now when it cuts the rope, what will happen? It will start to accelerate with 9.8 meter per second square. Okay, it will start to accelerate when the rope is broken. Okay, now just imagine or just hang a pendulum inside the lift. Okay, the pendulum inside the lift. Now let's take an observer X inside the elevator or lift, and observer Y outside the building or outside the lift. Now here, what we are going to study, the motion of this lift from the top floor of the building to the bottom, and same event is getting observed by this observer inside the lift and this observer outside the building. Here now let's take observations of observer X. Okay, observer X. What the observer X will observe? He will observe that the pendulum is at rest. Okay, what are the forces acting on the pendulum? The upward tension force by the spring, let's say T. Okay, let's say T, and the downward gravitational force G. Okay, or we will say here omega. Okay, the force acting on this pendulum, and upward force is tension force. Now according to him, as he is inside the lift, he does not observe, he cannot observe the motion of the pendulum, okay, from top floor to the bottom floor, or acceleration of that pendulum from top floor to the bottom floor. Okay, so he will note his observations as the pendulum is at rest, or it is not moving, or it is not accelerating. He will note down his readings as T, like tension force, minus omega, that means is equal to 0, because there is no net force. According to Newton's first law, if there is no motion, there is no force. Okay, so Newton's first law is not valid here. According to Newton's first law, the force or the motion is 0 here. Okay, or acceleration is 0. We can say acceleration is 0. So according to this observer, there is no force acting on this pendulum, because the force is balanced. We can say here P is equal to omega. So there is no force, and hence there is no acceleration. Now what the observer Y will observe? He is observing that the lift is falling, and hence the lift is accelerating. Why? Due to the acceleration due to gravity. And he will observe that the pendulum is hanged to the left, and hence the pendulum is also accelerating with the 9.8 meter per second square. So what are his readings? According to Y, he will observe that T minus omega is not equal to 0, or omega minus T is not equal to 0. That means there is some force, okay, some force on this pendulum, because it is in an accelerated motion. Okay, so acceleration is not equal to 0, is not 0. Okay, so according to X, there is no force on pendulum, and according to Y, there is a force on pendulum. So both of these observations are of a same event and at the same instant of time, and hence these both cannot be corrected simultaneously. So one of the reference frame we are using, or the observers are using, is not correct for the Newton's law to be correct or to be valid. Now here the lift is a non-inertial frame of reference, because it is in accelerated motion. We will see what is non-inertial and inertial frame of reference in detail, but now for time being, let's say let's get the introduction. The lift is a non-inertial frame of reference, and the Earth, the observer on the Earth, and hence Earth is a inertial frame of reference. Now let's take a look what are the inertial and non-inertial frame of references. So first, inertial frame of reference. Inertial frame of reference. In the last example, we have seen the Earth is at stationary or at a moving with a constant velocity, and hence it is a inertial reference frame. Inertial reference frame always at a rest or moving with constant velocity or uniform velocity. And similarly, we will say that side by side you will get the correct idea. Non-inertial frame of reference. Non-inertial frame of reference. Now, what is the inertial frame of reference? It is in a rest, at the position of rest or moving with constant velocity or uniform velocity. For example, Earth. Okay, Earth. Or a train is moving with uniform velocity is also a example of a inertial frame of reference, because it is in a uniform motion, it is not accelerating, or Earth at a rest is also a inertial frame of reference. What is the inertial frame of reference? Inertial frame of reference is a reference frame whose acceleration is 0. Okay, very simple. Whose acceleration is 0, and non-inertial frame of reference is what? Accelerating frame of reference, or whose acceleration is not equal to 0. There is some acceleration. Okay, non-inertial frame of reference is accelerating frame of reference. Accelerating frame of reference, and hence, for example, if a train, this train, let's take this train is moving with constant velocity. Now it will accelerate. Okay, it will accelerate, and as it is accelerating, it will change its velocity, and hence it has become non-inertial frame of reference. When the train was moving with uniform velocity, it was inertial frame of reference. But when the train is accelerating, it is non-inertial frame of reference. Okay, so these 2 points are very complicated and confusing. So just remember, what is inertial frame of reference? If the acceleration is 0, this is a inertial frame of reference, and acceleration is not 0, there is some acceleration, then this frame of reference is a non-inertial frame of reference. In last example we have seen Earth is the inertial reference of frame because it is at absolutely, or we can say the motion we neglect, but the Earth is at rest. Okay, and the lift was a non-inertial frame of reference because it was accelerating, and the readings of x are not valid according to Newton's first law of motion, and the readings of y was accurate to the according to Newton's laws of motion, because this reference frame, the Earth, is inertial frame of reference. So Newton's laws to be valid, we need inertial frame of reference, and if it is a non-inertial frame of reference, we have to introduce additional force which is called fictitious force or pseudo force, or we can say imaginary force, which is a not real force. Okay, for example, let's take example for the fictitious force. We have understood inertial frame of reference and non-inertial frame of reference. What is inertial frame of reference? It is at rest or moving with constant or uniform velocity but not accelerating, and non-inertial frame of reference is accelerating frame of reference. If there is acceleration in the frame of reference, then this is a non-inertial frame of reference. And now we will see what is a fictitious force or pseudo force. For why we need these two forces? Because in non-inertial frame, the Newton's law is not valid. We will see this example, but just know this. In non-inertial frame of reference, Newton's law is not valid, and hence we have to introduce fictitious force or pseudo force to Newton's law to be valid. Okay. So let's take an example of non-inertial frame of reference. Okay. Inertial frame of reference is very easy. In a state of rest or in a state of uniform motion. Okay. Let's take example of a non-inertial frame of reference. And in this example, we will see what is a fictitious force or pseudo force. Now, just consider a train. Now we will consider it is moving with uniform velocity. This train moving with uniform velocity. Okay, I will not write this. Okay, so it is moving with uniform velocity. Now inside here, let's consider observer X. Now when the train is moving with uniform velocity, it is inertial frame of reference. Okay, now the person will not feel any force. Okay, now what will happen when the train or the train driver applies brake on the train? Okay, when the train driver applies brake on the train, that means force on the train, and hence the train will decelerate, or its acceleration, its velocity will change, and it will be in an accelerated motion. Okay, so now as the brake is applied, there is a deceleration, or we can say change in velocity, that is acceleration, but in a negative acceleration. Okay, you can understand this. Now when the train is accelerating, it is in a non-inertial frame of reference. Now this observer will feel a force. Okay, he will get, now when the brake is applied, the person will get pushed forward. Okay, pushed forward. When the train was at uniform velocity, he will not feel any force, but when the train is in a when the brakes are applied, he will feel a forward push. According to Newton's law, if there is no force acting on this observer, he does not have to change his position. So when brakes are applied, the train changes its position. Okay, and the observer gets pushed forward, but there is no force acting on this observer. There is force applied on only train, and hence the Newton's law is not valid in this case. That means non-inertial frame. Now we have to introduce an additional force, fictitious force, to Newton's law to be valid. Fictitious force or pseudo force. When we add this force, the Newton's law is valid in non-inertial frame of reference. Now, so this is a fictitious force or pseudo force, which is not real force. Let's take another example. When the train is accelerating, now we have taken the example of a deceleration. Now the train is accelerating, the person or the observer will get backward push. Okay, so this is also a fictitious force, because there is no force applied on the observer. There is force applied on the train. Why this happens? Because his inertia. Okay, so he gets backward push, and as Newton's law has to be valid, there must be a force acting on the observer, but we are applying force on the train, not on the observer, but the observer is moving. According to Newton's first law, this cannot be correct, and hence why do we conclude this? Because we are in a non-inertial frame of reference. So this is about non-inertial frame of